So this particular set of graphs you've actually seen before. We used them in a problem earlier. I can't remember if it was on the homework or if it was an example problem, but we have used this before. But now I'm going to ask some different questions about the same set of graphs. So here, the graphs of f and g are shown in the interval from 0 to 5. Let k be this function defined by k of x equals 4 minus f of x times g of x. Consider x equals 2 and x equals 4 and determine whether k is continuous at either of these values. Justify your answers using correct limit notation. All right. So I'm going to start at 2 for x equals 2. We're going to start considering that. Remember, in order to be continuous, 3 things had to happen. What are the 3 things that have to happen? As x approaches 2 of f of x, so let's say the whole thing. What else has to be true?
f of 2 has to be equal to the limit of x approaching
It's okay. It takes a while to get to where it can just blah, 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 trip off your tongue.
Is it the limit as x approaches 2 of f of x is equal to f of c?
F of 2 here, right? So the function has to exist as x at this particular x value. The limit as x approaches this x value of f of x has to exist, and they have to be equal to each other. Those are the 3 things. So first thing I'm going to do is figure out, well, what is f of 2? Oh, sorry, not f of 2, k of 2. My fault. We want to know if k is continuous. K of 2 is going to be equal to 4 minus, what is f at 2? 4. Times, what is g at 2? Also 4. 4 minus 4 is 0, times 4 is 0. So the function exists, the function k exists at x equals 2. All right, that's step 1. Step 2, I need to find, does the limit exist? And almost always on these, it's best to just go ahead and start with looking from the left and looking from the right. Because if the limit from the left and the limit from the right disagree with each other, then the limit doesn't exist. So the limit as x approaches 2 from the left of k of x is going to be equal to 4 minus, as x approaches 2 from the left, what does f of x approach? No?
Oh, wait, 2.
It approaches 4, right? Times, as x approaches 2 from the left, what does g approach? -1. Fortunately, it's 0 times something, so that turns out to be 0 also. So I'll keep going. The limit as x approaches 2 from the right of k of x is going to be 4 minus, as I approach 2 from the right, f of x approaches 4. And as I approach 2 from the right, g of x also approaches 4. But we've already showed that that's 0. So that means then that the limit as x approaches 2 of k of x is equal to 4, or should be is equal to 0, which is what we found for k of 2. So k is continuous at x equals 2. All right, let's see what happens at x equals 4. So I'll find k of 4. k of 4 is going to be 4 minus, what is f at 4 equal to? 3 times g at 4. What is g at 4? 1. So that's 1. So the function exists, the function k exists at 4. I shouldn't say the function because we've got 3 functions going on here, right? It's one of those things where you have to be careful to identify which one you're talking about. All right, so let's do the limit as x goes to 4 from the left of k of x. So that's going to be 4 minus, as we approach 4 from the left, f of x still approaches 3. As we approach 4 from the left, g of x approaches what? 1. And we've already showed that that's 1. Like, great. This looks like it's going to be continuous. Not so fast. The limit as x approaches 4 from the right of k of x, though, still going to be 4, because that's a constant, minus, as I approach 4 from the right on my graph of f, I'm approaching 3. They're like, this is going to be exactly the same. Right here at the end, as x approaches 4 from the right, g approaches 4. So, the limit as x approaches 4 of k of x does not exist. Therefore, k is not continuous at x equals 4. All right. Fortunately, part B of this takes almost no time at all. Values of f of x, its selected values of x are given in the table below. Based on the values in the table, what's a reasonable estimate for the limit as x approaches 1 of f of x? Well, it's somewhere between these two values, right? You could give any value in between those two values that you wanted to get. I usually split the difference. But it doesn't matter. If you gave me 2.785, that would be fine. If you gave me 2.786, that would be fine. I usually say that it's probably halfway between those. Looks like it's going to be 2.7855. So if that really is true, what kind of discontinuity do we have here? The limit from the left and the limit from the right are the same. So the limit exists, both from the left and the right, but the function doesn't exist at that point. What kind of a discontinuity is that then? Yeah, this is a removable discontinuity. It's removable because the limit as x approaches 1 of f of x exists, but f of 1 does not exist. It can be like that. This is your classic hole in the graph. There's just a point missing. The other way you could have a removable discontinuity would be if instead of this being undefined, this was like 12. So instead of being where you want it to be, it's somewhere way up higher. That's also a removable discontinuity. Okay, moving on. So this is one that I got off of AP Central. It is known that the limit as x approaches 0 of sine of 2x over 2x is equal to 1. Shouldn't come as a big surprise to us. what's the limit as x goes to 0 of tangent of 2x over 6x secant of 3x? And you're like, oh, holy cow. How am I supposed to get that? Well, again, just like I was saying earlier, I'm going to rewrite everything in terms of sine and cosine, because I'm a lot better with those. So this is sine of 2x over cosine of 2x over 6x, and secant is of 3x is equal to what? 1 over cosine of 3x. I can do a little bit of cleanup immediately, because as x goes to 0, what does cosine of 2x go to? Nope. Try again.
0.
Nope. 3 strikes and you're out. 1. Cosine of 0 is 1. And sine of 2x divided by 1 is just sine of 2x. So that's going to be the limit as x approaches 0 of sine of 2x and in the denominator, as x goes to 0, what does cosine of 3x go to? 1. So that's 1 over 1 is 1, so this is 6x. You're like, well, it's not quite what I want it to be. I'd really like it to be the limit as x goes to 0 of sine of 2x over 2x. A little bit of algebraic manipulation. This would be sine of 2x over 3 times 2x. So this part, we were told, goes to 1. This whole thing goes to 1/3. Questions? All right, let's move on then. This is another one that I got off of AP Central. And the reason I'm mining so much stuff from there, I usually get stuff out of our textbook, but the reason I'm mining so much stuff for that is, again, last year my AB students, limits was their worst topic. Wasn't that they were horrible, but it was just the one that's kind of stuck out as, wow, that one's not as good as all the other ones. So I'm like, let's do some ones that they say are ones we ought to do. All right, so here's the deal. This whole absolute value thing, you're like, can I just cancel those? No, you cannot. Because this isn't just x minus 2. So I want to find the limit as x goes to 2 of f of x. That has nothing to do with what it is at 2, does it? So I'm going to look from the left and from the right on this. So the limit as x goes to 2 from the left of f of x. That'll be the limit as x goes to 2 from the left of x minus 2 quantity squared times sine of x over, and this is where you have to start thinking. I don't want to just put the absolute value of x minus 2, because I'm never going to be able to cancel that. If I have a value slightly less than 2, and I substitute it into the absolute value of x minus 2, what is the x minus 2 going to return, a positive number or a negative number? No, not with the absolute value, just the x minus 2. It's going to return a negative number. To make it positive, I'm going to need to take the opposite of that. So this is going to be the opposite of x minus 2. Because when I take values less than 2, x minus 2 is going to be a negative number all the time. If I'm doing values of x less than 2, so I'm always going to need to switch the sign. Well, these happily cancel out, and I'm left with a negative 1 on bottom. Oh, sorry. Hang on a second. I drew the canceling wrong up here. He cancels one of those out. So now I substitute in the 2. I've got 2 minus 2 is 0 times the sine of 2. I don't know what the sine of 2 is, but 0 times whatever it is still 0. And the denominator is negative 1. And 0 over negative 1 is 0. It's like, don't everybody jump at once. Then we'll look from the right. The limit as x approaches 2 from the right of f of x will be the limit as x approaches 2 from the right of x minus 2 quantity squared times sine of x over, if I'm taking values of x bigger than 2 and subtracting 2 from it, what kind of values will I always get? Positive values. So the absolute value doesn't do anything to it. So this is just going to be x minus 2. Again, I can cancel those. As x goes to 2, that's going to be 0 times the sine of 2, which is 0. Over on bottom, we're left with a positive 1. And this happens to work out because both of the numerators were 0. So the limit as x approaches 2 of f of x is 0. What kind of a discontinuity do we have here? Well, the limit exists. So graphically, that means it's coming from here and coming from here, but the function doesn't exist. What is that? Yeah, it's a removable discontinuity. Because the limit as x approaches 2 of f of x is equal to 0, but that's not equal to f at 2 because that's equal to pi. Okay, I'm going to try and rocket through one more example. Sorry that we're not going to get to all of them, but this is an important idea. So if I'm trying to take the limit as x goes to pi over 4 of this, what is cosine at pi over 4? Pardon? Yes, square root of 2 over 2. Sine, also square root of 2 over 2. So when I subtract that, that's 0. And then 1 minus 2 times the square root of 2 over 2 squared. You're like, oh, that's a lot of 2's. That's 1 minus 2 times the square root of 2 times the square root of 2 is 2 over 4. That's 1 minus 4 over 4. That's also 0. So I have an indeterminate form. When I have an indeterminate form, I need to do something to make it not indeterminate anymore. What I'm going to do is this. Remember I said I don't think you need to know all the identities that you learned in pre-cal, but you do need to know the Pythagorean identities. I'm going to replace 1 with sine squared x plus cosine squared x. What was my hint? Well, there were two of them. One is that it had a 1 in it, and I know that that's sine squared plus cosine squared. But the other thing is it had a sine squared term in it. So that'll be the limit. As x goes to pi over 4, I'm going to do this as quick as I can. Cosine x minus sine x. Down here, I'm going to have cosine squared x minus sine squared x. It's still 0 over 0 because I haven't been able to cancel anything yet. I'm just going to show you this one more step. Cosine x minus sine x over, I can factor this to cosine x plus sine x times cosine x minus sine x. And now I can reduce that. And now it's not 0 over 0, so we can just do a direct substitution. We can evaluate that function. All right. Thank you. Y'all have a great day.